Fish have been swimming in the seas of our planet for hundreds of millions of years, so it's no surprise that they're really efficient at it. Engineers know that there's no point in reinventing the wheel, so they've started copying the supremely efficient designs of nature. That's how come we have a tuna called Charlie, the first robofish, swimming in a tank at the Massachusetts Institute of Technology. There are many good reasons why scientists there are trying to copy fish. Your average fish can do a U-turn without slowing down, whereas a ship has to slow down by over 50% to reverse its direction. And fish can do their complete U-turn in a very tight curve, with a radius only about 1/5 the length of their bodies, while ships need to have a curve 10 times larger. A very maneuverable ship could avoid many accidents. Like fish, dolphins are remarkable ocean-going creatures. They can produce about 4 horsepower and can travel at 80 kilometers per hour, but if we want a boat to travel at that speed, we have to give it a 70 horsepower engine. Each year, billions of tons of goods are moved across the oceans by large ships. If we could increase their efficiency, it would mean an enormous saving in fuel costs. And of course, there are the military applications. Propellers are noisy, and the Navy would like quiet ships. These reasons, maneuverability, efficiency, and low noise, are just a few of the reasons why Charlie the robofish was invented. Why is a fish much more efficient at moving through the water than a ship with a propeller? Well, a propeller creates a long spinning stream of water called a vortex that stretches behind the ship, robbing energy and slowing the ship down. But the flapping tail of a fish is quite different. As it sweeps to one side, it creates, say, a clockwise spinning vortex in the water. But when the tail flips back in the other direction, it creates a counterclockwise vortex. The next step is the key to the efficiency of the fish. The counterclockwise vortex runs into the clockwise vortex, and when they meet, they force water away from the fish. Newton said, "For every action there is an equal and opposite reaction," and so, if the water is forced backwards, there's a reaction that pushes the fish forwards. Because of this marvelously simple mechanism, fish use hardly any energy to move through the water. Even an early artificial fish like Charlie the robofish can achieve 86% efficiency, while the best that our ships can achieve is 40%. Of course, fish use extra tricks besides just flapping their tails. They also flex their bodies, so they can even extract energy out of the vortexes that roll down the sides of their bodies. However, making an exact copy of a fish, with a smooth and flexible body, is way beyond what we can build into the robots of today.